Hey, today I have the pleasure to host for the first time Kent Martin. Hi, Kent.
Hey, Youssef, how are you doing?
All good. Very happy to have you with me. But first, introduce yourself.
Yeah, my name is Kent Martin. I'm a product manager here at Databricks. I've been at Databricks now for almost 4 years. And in that time, I've owned the things that we've built related to geospatial, but also have supported teams that have worked on Photon, predictive optimization, and more recently in the last year, taking ownership over the SQL language surface area. So I work with the teams that are building out SQL scripting, stored procedures, collations, all those kinds of features.
And since you mentioned those features, we already recorded many sessions on store procedures, recursive cities. So if you have time, go check them. And today we're gonna be talking about geospatial. What's geospatial? What are the new features that Databricks released?
Yeah, of course. Yeah, geospatial, big umbrella term. It can mean all the things related to the location of objects in the world, the representation of the physical world. But basically, everything on the planet has a location, right? If you're, let's see, a person, if it's a vehicle, if it's a device, if it's, anything like I can look outside my windows here and see trees and streets and light posts. All these objects have a location and they all are connected to each other in some way. And depending on your business, which may be, across any industry, location matters, right? I mean, we're not just talking about real estate. So we have customers who care about, autonomous vehicles, and they track vehicle movement. They look at ways to increase and improve, safety, to improve the driving experience based on, cellular signals and what's connected in the car. All of this is driven by an understanding of location. So for anyone who's doing, anything related to mobility data and the movement of goods or people, they're going to work with location data and need to work with those with that data in a way that's efficient, because geospatial tends to be a little bit bigger data when you start talking about how things are modeled in the world. So for boundaries and things that belong to networks like roads or pipelines or cable networks, all these are modeled as linear objects or polygon objects, like the actual primitives. And that can sort of add up to larger data sizes. And we can dig into sort of what that looks like in the demo as well. But basically, geospatial is just thinking about how to understand how location impacts your business. Now, you asked about what's new in Databricks. Maybe I can take a little step back and just sort of lay out how customers have been successful on Databricks over time with working with geospatial data. And the truth is, Databricks is a Spark platform, and the Spark ecosystem and common libraries used by data scientists have all worked on and in Databricks for the longest time. So there's been like a choose your own adventure kind of approach to working with geospatial data. So you might use Apache Sedona or GeoPandas or these other libraries. These are certainly the right tool for the job at the time. What we've released is support for two new data types, geometry and geography. So these are purpose built for storing vector spatial data. We've also released over 80 expressions. They're all SQL expressions, but they're also available in Python and Scala. So there's appropriate data frame APIs to work with these expressions. Then on top of the types and the expressions, the one of the common things that people do is do spatial joins, which is basically a way of understanding spatial relationships or spatially aggregating data. You might think of it as counting, the number of events within a boundary, right? Points inside of polygons. And so with our implementation, we've really built a highly performant spatial join, which is great for anyone who's doing that kind of aggregation work. So we have types, expressions, really fast spatial joins. And I'll also say, like, we haven't built everything, but there's certainly a lot more to come.
And that's out of curiosity. I remember In the past, we used to have a library called, or maybe a framework called Mosaic. So we do not have to confuse it with Mosaic ML, which is, or Mosaic AI. That's another, let's say, offering from the acquisition of Mosaic ML. So is it something that's, what's the difference between this framework and what Databricks released recently?
Yeah, that's a great question. So when we talk about any of these, libraries or frameworks that have existed where customers have used to do this kind of work, what I'm saying now is there is in the Venn diagram of what's supported between those libraries and what we've built, there's a lot of overlap. And if you're doing anything with native SQL, native types, you should just use what's built in to Databricks. There's a number of benefits that are going to result from using these types and expressions related to performance and efficiency. Mosaic was a Databricks Labs project driven by some of the geospatial subject matter experts in the field. And basically, they built out a framework that basically could get the most out of Databricks. So it was tightly integrated with new features that were in the platform. With Mosaic, we offered vector, raster, and grid indexing functionality, which is fairly commonly used across all of our customers. But what the vision was for Mosaic was we really wanted it to be a bridge to what we built into the product. So we could accelerate in a Databricks Labs environment because there was such a need for customers to solve geospatial problems that the field was kind of innovating and trying to move quickly and built out this library for customers to use. And then working closely with the folks who were driving Mosaic and myself, we collaborated on what was most important, kind of learned from how Mosaic was being used. And this led to, what we ended up building natively in the product. So Mosaic is sort of reaching an end of life, right? As we, I think the last version Mosaic is supported on is DBR 13.3. So this is quite some time ago. And Databricks Spatial SQL, this is the sort of product offering we now have, which are the expressions, the types, the joins. It's all one big thing called Spatial SQL. This was first available in private preview late in the 14 series, but now we've all kind of accelerated through the preview phase. We're in public preview now as of DBR 17.1, and we're looking to help customers transition to this solution on the platform.
And maybe let's move to the demo.
Yeah, you want to see a little bit of it in action? Let's do it.
Yeah.
All right, Yusuf, I've got this demo pulled up here. Let me just reset a couple of things. Oh, these are the previous results. I previously run this code just to make it sort of simple to walk through. So, all this stuff ran. I was running it, I think, in the last couple of days. This demo looks at and works with a couple of data sets. One is the UNESCO World Heritage Sites. So these are like, important places in the world that people care about, that we should cherish and protect. And then a set of boundaries within the country of Italy. We picked Italy. One of our good friends, went to Italy recently, and we can kind of use this as like a fun way to look at spatial data and some of the features that we're using, that we've released. So in this example, we've pulled open data, which is also good because anyone can go pull this data and experiment themselves. We could also share these queries or build it out in a notebook that we can share as well. And the key thing here is we're going to use a new expression called st_point. St_point is going to take a latitude and longitude and turn it into a point geometry. And from there, you're basically working with a native geometry type. So in this data, you can see what some of the UNESCO data looks like. It's pretty verbose with the description. I'm just going to minimize that. You can see, we've parsed this data, basically bringing it out into a table. And then if I come down here, the key line is using st_point, now a native function. I'm taking the longitude and latitude that came with those sites. I'm supplying a spatial reference identifier. All your geographic information needs to be within a spatial reference, and you should supply a spatial reference identifier. 4326 is one of the most commonly used, not always the most appropriate, but again, we can kind of dig into spatial reference systems as we build out more documentation around the feature. So in this case, we're using 4326, and then I can go ahead and let's look at the table results and see what we have. So here we have a new site geometry column, right? This includes and displays that spatial reference identifier and also shows you the latitude and longitude in a well-known text format. So this whole format of the data here is very human readable. This is actually extended well-known text by including the SRID and the actual geometry description. But the data is stored in a binary format. So this isn't the way in which the data is actually processed. It's processed in a much more efficient manner. So, okay, we have our world heritage sites stored as geometries. Great. Now let's look at those Italian regions that I was talking about. So with the World Heritage Sites, we have a collection of points. And now with the Italian regions, we're working with boundary data. So boundary data is going to include a larger number of coordinate pairs that represent each vertex within a polygon, each vertex within the boundary. And so in this case, again, we've just loaded the data, but we're using a different function. The open data in this case was provided in GeoJSON, and we have a number of expressions that allow you to easily import spatial data from these common formats. So the common formats being well-known text or well-known binary or GeoJSON, or of course latitudes and longitudes. All of those can be easily imported and brought in to a table. So again, similarly, we have the region geometry, which includes this full description of the boundary. It's in the same format here displayed. Okay, we've now got some points. We've got these polygons. We might start to ask some simple questions, and I'll just go ahead and jump into one of those. So if we wanted to ask which regions have sites and do a very basic sort of accounting for the World Heritage Sites within each Italian region, we can run this simple query, which does a spatial join. So here I'm taking the site and the region, running this st_contains operation. So for spatial predicates, we support st_contains, st_intersects, which are probably the most common, but of course we also support touches and equals and these other spatial predicates that you'll find commonly with any kind of database system that supports Spatial SQL. So yeah, we can go ahead and run this query. Here we're looking at the fourth result, and so we can see the sites and actually come back here. Yeah, I can just see like the region that these sites are actually located in. So here I can see the region names. My Italian geography not so great, but here they are here, and we've matched up our regions within these. We've matched up our UNESCO heritage sites within these regions. I will say, like, this is a pretty simplistic example, but most customers are going to work with sort of large scale mobility data. We have customers who work in agriculture, who work in energy, who work in distribution, whether that's like large scale global logistics or that's something like food delivery services like DoorDash or something like that, where they might be aggregating data in different ways, but working with larger scale data. And they're also going to care a lot about proximity and distances and things like this. So let's look at a couple ways in which we can look at measurements of spatial data. Again, fairly simplistic example. If you wanted to understand which region in Italy had the sort of highest density of World Heritage sites, largest number of sites given the area of the region, how could you do that? I'll just highlight a few of the key expressions. So there's ST area. We of course have other measuring expressions like ST perimeter, ST length, ST distance, and a few other varieties of calculating distances. So here I can run ST area to calculate that. I can also look at and calculate the density of the area. And then I'm going to look at actually calculating that area based on two different approaches. So one, when I use the region geometry, this is the actual geometry field that we looked at earlier that uses the spatial reference identifier 4326. That spatial reference system stores data in degrees. And so when we pass in this geometry into this ST area function, it's going to return the area in degrees, which most human beings do not use and is not like the standard way, but it's doing what the data provides. But we do something a little smarter when working with geography data. So we've talked about geometry and geography, which is probably worth its own explanation. Geometry, computing data and calculating data on the plane, and geography, looking at data on the sphere of the Earth. So accounting for the curvature of the Earth. In this case, if we actually cast to use geography, we automatically know that we should probably return this data in meters. And so we do that in this case, or we can compute it also in kilometers just by applying a factor. So here we have area provided in degrees, meters, and kilometers. Again, easy to compute these kinds of area calculations just by using the built-in functions. Awesome. So we've done area calculations. Let's take a quick look at the data in Italy and address one other issue that comes up with most customers' data, which is the projection, right? The actual spatial reference system. In this case, we're looking at uh, the Italian regional data. And instead of using a global spatial reference system like 4326, we can use a local national reference system, which is using the 6875. Not, I don't know this like off the top of my head. We got to look it up too, right? Like most
Yeah.
people don't have a bunch of SRIDs in their pocket. Um, but here in this case, we're going to use an Italian spatial reference system. And when you do that, you can go ahead. In this case, I'm looking at seeing um, which or which UNESCO heritage sites are within a kilometer of each other. So I can use a few of the built-in expressions to answer this kind of question. ST_buffer can create a buffer around a point. ST_transform is actually used to transform the global spatial reference system to the local projection. And this will affect the way the computation works for this data now. So if I go ahead, I'm just kind of come down here to the end part. We've buffered the sites. Now I actually want to run the intersects again in this case to see which sites overlap. Um, I also want to, let's see, if I want to actually compute the distance that's based on this projection, I can go ahead and use ST_distance. I think this is the last function we wanted to cover in the demo. And using this distance on the projected data versus the distance uh, on the global spatial reference system, you can see the difference between the two. And we have a number of expressions for calculating distance as well. So there's ST_distance sphere and ST_distance spheroid. Again, these are sort of like how accurate do you want your distance calculations to be? Some will use an actual sphere, some will be based on the actual ellipsoid of the Earth, so getting a higher precision, which might have a trade-off in the actual performance of the calculation. But in the end, I want to just show like when you're using a specific projection, which is going to use when you're calculating the distance is going to use the sort of the plane, the Cartesian um, uh, distance measurement. In this case, there's not really much difference between using the spheroid and sphere, and it's kind of a moot point. I kind of got away from the sort of main question I was asking here, which is which World Heritage sites are close by. But we have the Botanical Garden here, and there's a 14th century fresco that are very close by. Okay, Youssef, I may have lulled you into sort of the depths of spatial here, but that's okay. What I think is important about Spatial SQL is there are now ways where you can easily look at spatial relationships, spatial proximity, manage the correct reference systems for your data, and easily convert between geometries and geographies. And so it's just important for folks to know the trade-offs between calculating things on the plane and calculating things on the sphere. And of course, we're going to have more documentation that details this. So maybe this is a good time to kind of give a quick little overview of the docs where we can point people to it. Does that make
Yes.
sense?
Yeah. No, the
Yep.
documentation, the link will be in the description. You're going to have a bunch of more than, I think, 70 functions that you can use in SQL and also in Python and Scala, as Kat mentioned at the beginning of the session.
Yeah, so I brought up the doc page, a quick coverage of this. You can just use the table of contents here on the right, and you can see import. I talked about creating geometries from well-known text or GeoJSON. Again, looking at measurements, spatial reference related functionality. Look through the whole list. There's lots available in here. The docs all include a specific example. So if I go to ST_transform, I get specific examples on how to work with it, which is great. The other two things to call out in the docs, we also have details on the geometry data type, the geography data type, and in the next, or at least at some point here in the near future, there'll also be a blog post. So stay tuned for that. I think that's all I wanted to share on Spatial SQL and giving a quick overview. But I know that there'll be more content, more examples, and certainly a lot more excitement coming around this feature in the near future.
Awesome. Thank you so much, Kent.
Hey, thanks to you, Seth.